Today we'll be creating this 2D fluid simulation in Blender using geometry nodes. We'll be using the 3.5 alpha simulation branch, so there'll be a link in the description if you want to find a build for that. Also in the description is a link to the project file on Gumroad, so check that out if you'd like. And without further ado, let's get into it. To begin, let's do a quick overview of all the major steps in the process, and then we'll delve into the details. The objects in our scene include this fluid grid object, a collider object, and a particles object. The fluid grid object actually houses the simulation node network for the fluid simulation. The collider is just an object that is represented by a sphere, which has some drivers that animate its movement and change the velocity of the underlying grid based off of its change in position over time. And then the particles, which are hidden now, are going to be advected by the velocity field of the fluid grid and give a nice looking animation that will produce our final result. So to begin, let's look at the all-important fluid grid simulation geometry nodes network. First, you have the initialization of the grid, which involves first creating a grid mesh geometry with a resolution of 128 by 128 vertices, and then you store your neighbor coordinates. The reason that we're storing the neighbor positions for each point is because at various points in the simulation loop, we're going to want to be able to quickly reference and sample attributes from the neighbor locations. So instead of recalculating those every time we want to use them, we'll just store them as named attributes for quick access. So the way that we do that is first we just find the distance between any given neighbor point on the grid. The way that you do that is you take the resolution that we set in this outer group, you subtract 1 from that, and then you take 1 divided by that value. So that'll give you the length in between grid points, and then we just need vectors that point in each of the 4 different directions to the 4 different neighbors. So we use a combine XYZ node for that, and so for the right-hand neighbor, that's just the length piped into the X component. For the left neighbor, that's just the X component being the negative length. For the up and down neighbors, it's just the same as the left and right, except for you're piping the length and the negative length into the Y component of the combine XYZ. So now we have these offset vectors in each of the 4 neighbor directions. And then we use this store neighbor position attribute node group, which takes in the name of the attribute that you want to store. And if we hop in there, we can see that it stores that attribute as a vector attribute on the geometry. And it takes the offset vector, it adds it to the position of the grid point in question, and then it wraps that value from negative 0.5 to 0.5 in both the X and Y axis. And so what that does is it just wraps the neighbor around the boundary of the grid. So if you're on the side, on the edge of the grid, then your right neighbor over here doesn't exist. So instead we just wrap around and make sure that your neighbor is actually on the other side of the grid. Switching back to the outer network, we move on to the initialization of attributes. We initialize attributes on each point of the grid for the grid color, the velocity, the divergence, and the pressure. Pressure and divergence are floating point values on each point, while velocity is a 2D vector, so we're only using the X and Y components of this vector, and the grid color is a color. The pressure and divergence attributes are initialized to 0, while the grid color is initialized to this checker pattern, which you can see in the preview window here. And the velocity attribute is initialized just to 0, 0 in this case, but I also have this unconnected initialization, which creates a random noise texture initialization so that you get a little bit of change in the grid over time straight off the bat. If you don't have that connected, then The only thing that changes the underlying velocity field is the collider as it moves. For a little theory on the fluid simulation algorithm, we should first note that fluids such as water are essentially incompressible, meaning that for each point on our fluid grid, there should always be just as much fluid entering it as exiting it. Divergence is the net amount of fluid entering or exiting a point on the grid at any given point in time. So for our fluid to be incompressible, we must ensure that the divergence at each of these points is 0. In nature, the pressure of the fluid is what keeps it divergence free. So without going too deep into the math, we can use the Navier-Stokes equations for incompressible fluid flow to create an algorithm to calculate the pressure of each grid point so that the divergence stays at 0. We'll be using an iterative method to reach this solution, so the results get more accurate the more iterations we do. At the cost of exact accuracy, we can keep the iteration count relatively low in order to keep the simulation time in check while maintaining a visually appealing result. So with that, we can dive into the actual simulation part of this node network. So the major steps within the simulation loop are we are going to set the collider velocity. So that's the velocity of the sphere over here that moves around in a specified path. Then we set the collider color. So what that does is you'll see that as this collider moves around the grid, it's dropping some color down, and this node group handles the creation of those attributes. Then we'll advect the velocity. So advection is really just taking a point on the grid and then using its velocity to look in the opposite direction of its velocity. So if its velocity is up and to the right, we're going to look back and to the left. And then we're going to take the velocity that's stored at that point and we're going to make it the velocity of the original point. So then over time, the actual velocity of the fluid changes itself and it moves along the paths that it defines on its own. Then we'll calculate the divergence. So this is just a way of calculating the amount of fluid that after the velocity advection step is entering or exiting each point on the fluid grid. Then we calculate the pressure, which we talked about a little bit just a second ago, and we use an iterative approach here that you can see in these 16 steps to converge on a solution for the pressure that makes sure that this divergence ends up being 0. Then we subtract the pressure gradient from the velocity field, so we use the pressure attribute to figure out how we want to change the velocity field in order to make sure that the divergence is 0 instead of whatever the divergence is after this velocity advection step. And then we just advect the color. So just like we advect velocity, we're looking back along the negative velocity vector of each point on the grid. We're looking at the color at that surface point and we're moving that or setting the original grid point to have that color. After that, all we have left is to set the material to this grid material, which takes the grid color and displays it as an emissive material on the fluid grid geometry. And with that, we're done with the fluid grid simulation geometry nodes network. For a more detailed explanation, let's loop back around to the set collider velocity network. Opening that up, we see that what we're doing in this network is taking in the object info input node for the collider, and then we're subtracting the last position of the collider that is stored in an attribute from the current location as specified in this input node. And then we're storing that as the collider velocity attribute. So the last collider position that we're subtracting from the current collider position is set here. And you just pipe in the location of the collider object straight into that value. And since we're updating this attribute after we use the last collider position to update the current collider velocity, this will always be the position of the collider from the last frame. Then what we need to do is we actually only want to update the velocity of the grid to be the collider velocity if the position of the grid point in question is close enough to the collider. In this case, it's a sphere, and so I actually just have the distance test to be 0.05, which is a little bit smaller than the actual radius of the sphere, which I believe is 0.075. And so what you do here is you just take the position of the grid point, you find the distance from the location of the collider, and then you use this compare node to check whether or not that distance is less than a certain value, in this case 0.05, and then you use the switch node to set the velocity just to what the velocity already is at that grid point if this ends up being false. So the position of the grid point is farther away than 0.05, and to the collider velocity if it is closer than 0.05. So you just store that in the velocity attribute of the grid point, and you are done with this node group. If you then jump back out into the outer network, we can set the collider color, which does a pretty similar process where it's checking the distance from the object info collider node location and the position of the grid point, and if that's less than a certain value, in this case it is the radius of the sphere, that's 0.075, then you're going to set the color to a new color, which in this case changes over time using this scene time node. So I have the frame just multiplied by a small value, 0.01, and then I wrap that value between 0 and 1 so that this color ramp node, which is set to HSV and far, so it just cycles around the color wheel, so that you just kind of wrap around those colors over time, and then you set that to be the color if the grid point is within the radius of the sphere, of the distance to its center point. And then if it is farther away than that distance, you just set the color to be the same as before. I'm using this same node group within the particles node network. So what I do is I actually use a group input name to define the attribute name. So in this case it's grid color. In the particle node network it'll be particle color. So that's why this pipes in the name from the group input node there. And then you just store the output of that switch node as the grid color attribute, in this case, on the geometry, and that is it for that network. Jumping out of that, we then advect the velocity of each grid point. This is a relatively simple network, and really all it does is it takes the position of the grid point, it subtracts the velocity from itself. We actually wrap from negative 0.5 to 0.5, so that if you are a grid point that has, you're kind of near an edge and your velocity, the negative velocity actually ends up bringing you outside of the grid bounds, it then just sort of like wraps around to the other side of the grid, both vertically and horizontally. So if it was down like this, you'd end up in this corner up here. And that allows the advection just to keep all the fluid just sort of within these bounds and not colliding with them. I just like the way it looks, so that's the way I did it. Then you sample the nearest surface so that you can kind of interpolate between grid points. So if the velocity or the negative velocity of a point ends up being in the middle of a couple of different points, you don't want to choose the nearest one, you want to choose the interpolated value between the four of them. And so the sample nearest surface will just take care of that for you. And so we're just sampling the velocity attribute from that surface point. I have this scale set here, it's just to 1, but if you want to add some damping over time or some loss of momentum and velocity, you can set that to something like 0.96. And then as this simulation progresses, the velocity loses its momentum, rather than if you just have it set to be 1, it'll just keep on moving. And I like the way that looks, but I kept this scale node in there just to have the option. Then you just store the output of that scale node into the velocity attribute, and you are done with velocity advection. Jumping back out into the outer network, we can then go over the calculation of the divergence. Here we sample the velocities for each of the 4 neighboring grid points to the center grid point, and then we take the contributions of the horizontal neighbors and the vertical neighbors, we add them together, and then we average them out to get the divergence for the center grid point that then we store as the divergence attribute on that point. So the way that we get the horizontal contribution to the divergence from the velocities of the right and left neighbor points, what we do is we first sample the velocity of each of those neighbors. Then we use a separate XYZ node to pull out the X component of those, because we're only interested in the horizontal velocity, not the Y component, which defines the vertical component of the velocity. And then we combine those with the subtraction node, because the right neighbor, the X component, contributes positively to the divergence, because the divergence is defined as the amount of fluid leaving the point at any given point in time. And so the neighbor that's to the right of the center point, if it has a velocity with an X component that's positive, that's pointing away from the center point. But the left neighbor with a positive X component to its velocity is pointing inwards. And so the divergence is defined as outward, so we just need to multiply that by -1, or just subtract it from the X component of the right-hand velocity to combine it. We do a similar thing for the vertical contribution, just instead with the right and left neighbors, it's the up and down neighbors, and we separate the Y component out instead of the X component. And in this case, the neighbor in the up direction, the Y component, if it's positive, is facing away from the center component, and conversely for the down neighbor, the Y component being positive points in towards the center point. So that needs to be negative. Again, you subtract the Y component of the down neighbor velocity from the up neighbor velocity, the Y component of that, and then you just add those together to get the total divergence, but you still need to average them. So you just divide by 2, because you've got 2 components, divided by 2, and then you just store that as the divergence. So the way that we're sampling the neighbor velocity is we're using those named attributes that we set up before. So we have a name input here, which is the name of the attribute position for each of the 4 different neighbors. And so you just get the position of that, and then you sample the nearest point to that position on the same fluid grid geometry as the point in question. And then you sample that index that you get from sampling the nearest, and you sample the velocity from that, and then that's what you pipe into your output of that node group. So that's how you sample the velocity. So after we've calculated the divergence, we can then move on to calculating the pressure. Here, the first thing that we do is we set the pressure attribute to be 0. We do this in every iteration of the simulation because we want to start with a clean slate for iterating 16 times through the pressure iteration step to create a pressure value for each grid point that through the subtract pressure gradient step will end up with a divergence-free grid or close to a divergence-free grid so that we can maintain incompressibility within our fluid. So the pressure iteration step is actually pretty similar to the calculation of the divergence, or at least it looks very similar. And the way that it works is instead of sampling the velocity from the 4 neighbors, you're sampling the pressure from the 4 neighbors. So the pressure iterations the pressure attribute depends on itself. And so then you're just adding all of those up, and then you're subtracting the divergence from the accumulated pressure from the 4 neighbors, and then you average that out and divide by 4. So sampling the pressure is super simple to sampling the velocity. You just take in the named attribute of the neighbor, you find the index of the closest point on the fluid grid geometry, then you sample that index and you're reading the pressure using this named attribute node, and then that becomes the output of that node group. So then we add the pressure from the right and the left, and then we add that to the up and the down neighbors and just combine those with this add node, subtract the divergence, and then divide by 4, and then you pipe that into the pressure attribute, and you just repeat that a number of times. 16 times results in pretty good results, but you could add more if you wanted to get a technically more accurate simulation. So hopping out of that, we can move on to the subtraction of the pressure gradient, which is a super important step because that uses the pressure that we calculated in the last step to change the velocity of each of the grid points so that the divergence ends up being 0. Here we're undergoing a process very similar to the calculation of the divergence as well as the individual pressure calculation iteration steps. In this case, we're sampling the pressure from each of the 4 neighbors, and then we're combining that together into a velocity vector that is subtracted from the current velocity of the center cell, or the cell in question, and then that subtraction becomes the new updated velocity for the center point or center cell. So the way that you go about doing that is you subtract the pressure from the left cell from the pressure of the right cell, and then that value becomes the x component of the velocity vector defined by the pressure values that then you subtract from the velocity vector. The up and down neighbor pressures are subtracted, the down pressure is subtracted from the up pressure to create the y component of the vector that is then subtracted from the current point's velocity vector. And the reason that you subtract the left from the right and the down from the up is kind of similar to the reason you do it within the divergence calculation step as well, and that's that pressure is kind of an outward facing force from each of the individual grid points. So from the right neighbor, the pressure is pointing inwards towards the center cell, so it contributes negatively, and then the left cell is pointing from the left to the right in towards the center, so it's contributing sort of a positive velocity. And so then you might ask, why are we subtracting the left from the right and not the opposite? And that's a valid question, but it's basically solved by the fact that we're subtracting this vector from the current velocity vector instead of adding it. It would be equivalent to subtract the right from the left rather than the left from the right, and the up from the down rather than the down from the up, and then combine those in the same way if you changed this subtract vector node to an add. But this is the way that we're doing it. So you create this pressure-based velocity vector from the different neighbor pressures, and then you subtract that from the velocity vector, and that gives you the new velocity vector, which defines itself in such a way based off of these pressure values that were calculated in the iterative steps from the step before, so that the divergence is 0 and we get the all-important incompressible fluids. We already went over the sampling of the neighbor pressure, so I won't do that again. And after that, we can move on to the color advection, which is really simple and is basically exactly the same as the advection of the velocity. So what you do here is you take you subtract the velocity of the point in question from the position of the point in question. Then you wrap that value between negative 0.5 and 0.5 so that if you're on the edge, it wraps around to the other side. You sample the fluid grid mesh at that point, and you get the grid color attribute out of that, and then you store that sampled value as the new updated grid color, and that's what allows the color to advect over the simulation. As I mentioned before, we actually have this particles object which is currently hidden, and we've set this grid material, which if you look in the shader editor, go into the grid material, find that all it does is it creates an emission material node, shader node, and it pipes in the grid color. And this is really just what I use for debugging in the course of creating this simulation, and it can be helpful for that, so I wanted just to include it here. But really what we want to see in the final render is the particles. I'm going to switch to cycles, which will automatically render geometry for the particles, so I don't have to create it using instance on points. But I find this type of simulation to be pretty darn cool. And so now I'm going to go over how we create the particle advection animation. So if you hop into this particle nodes, geometry nodes network, what it does is similar to the simulation geometry nodes network for the fluid grid. It initializes a grid of geometry. So it uses the same mesh primitive grid node. The vertices are set to 512 by 512, so that's a lot higher resolution than the fluid grid. And then you convert those grid vertices to points. You store a particle color. I have it just set to this blue color here, but again, I have the option to set it to a checkered texture at the beginning, which will just provide a little bit of a different pattern that can get moved around. Just depends on what you like. I'm going to start with a solid color, and then you bring that geometry into the simulation input. And all you're doing here is you're sampling the velocity of the fluid grid and advecting the particles based off of the velocity of the closest points to the position of the particle. And then you're also wrapping the position of the particle similarly to how we wrapped the advection steps within the fluid grid simulation node network, so that if they go outside of the bounds, they just switch to the other side, and so you can just keep those particles within the simulation. So the way that you sample the fluid grid is you bring an object info node that is hooked up to the fluid grid object, and you just sample the nearest surface by the position, which will correspond to the position of the individual particle, and you want to sample the velocity attribute of that surface. So then you just set the position of the particle with an offset of the sampled velocity. Here is the wrapping. The wrapping functionality is just another set position node that just wraps the new position after you apply the velocity offset with a minimum of -0.5, -0.5, a max of 0.5. And that's the end of the simulation. We have this set collider color node network, which is the same node group as we have within the fluid grid node network, but instead of having an input that says grid color, it says particle color. And that works exactly the same described as before. So if you're within a certain distance of the collider, it'll set the color that sort of rotates around the hue wheel over time, and that's what creates these changing colors that you see around the collider as it animates. The last thing to go over in this network is just setting the particle material, which again is a super simple material, which is almost exactly the same as the grid material, except for it brings in a different named attribute, in this case the particle color instead of the grid color, pipes that into emission node, and there you have it. I'll also quickly go over the animation of the collider, which happens in two drivers on the X and Y location of the collider object. And the way that works is you've got the negative sign of the frame times 0.1 times 0.25, and for the Y component it's the cosine of the frame of 0.05 times 0.25, and that just creates a certain motion for the collider. You can set this to whatever you want. You don't need to use drivers to animate the collider object. You can animate it with keyframes. You can use constraints. You could use an armature if you really wanted to. Really doesn't matter too much, but this is a cool sort of procedural animation that you can use if you'd like, if it tickles your fancy or what have you. Really, it's just about, exploring creative avenues of thought, etc. And before I ramble too much, I'm going to sign off. I hope you enjoyed this tutorial. I hope you learned something, and above all, I hope you had fun. If you have any questions, feel free to comment. I would love to hear from you. And until next time, goodbye.